Our planet has a rhythm, a cycle of ice ages and warm interglacials, driven by subtle wobbles in Earth's orbit. These cycles have been a constant, a heartbeat of Earth, shaping the climate and life on our planet for millions of years, but sometimes, the pattern breaks. Between 800,000 and 430,000 years ago, Earth's warm periods were unexpectedly cool. This anomaly in the climate record has intrigued scientists for decades, prompting questions about the forces at play. This era, known as the Mid-Pleistocene Transition, puzzled scientists. Why did familiar solar cycles fail to bring the usual warmth? What hidden mechanisms were at work during this time? The answer lies not in the sky, but in the deep churning Southern Ocean. This vast body of water, often overlooked, plays a crucial role in regulating Earth's climate. During these lukewarm interglacials, atmospheric CO2 was unusually low, keeping the planet cool. This reduction in carbon dioxide levels was a key factor in the cooler temperatures. The mystery remains. Where did all that missing carbon go? Scientists have been piecing together clues to solve this puzzle. Clues point to the remote Southern Ocean, where powerful forces quietly regulate the planet's climate. This ocean acts as a giant carbon sink, absorbing vast amounts of carbon dioxide from the atmosphere. By studying ancient ice and ocean sediments, scientists discovered that the oceans, ice caps, and atmosphere are tightly linked. These connections are vital to understanding past and future climate changes. The Southern Ocean, though distant and wild, holds immense power over global climate. Its influence extends far beyond its icy waters, affecting weather patterns and temperatures worldwide. Its hidden processes can tip the balance between ice ages and warmth. Understanding these processes is crucial for predicting future climate scenarios. Understanding these past events reveals how fragile and interconnected our climate system truly is. The lessons learned from this era can guide us in addressing current climate challenges. The health of the planet can hinge on what happens in the cold, dark depths of the Southern Ocean. This remote region is a key player in the global climate system, and in those depths, the story of Earth's lukewarm pause begins. It is a story of mystery, discovery, and the intricate dance of natural forces that shape our world. The Southern Ocean is the windiest, stormiest, and most unpredictable ocean on the planet, where fierce gales whip up towering waves and relentless storms churn the waters day and night. It's also the most remote ocean on Earth, encircling the icy continent of Antarctica, far from the reach of most human activity. But the Southern Ocean isn't just a distant frontier, it's a global hub, seamlessly connecting the Atlantic, Pacific, and Indian Oceans, allowing water, heat, and life to flow between them. This vast ocean acts as the planet's circulatory system, pumping energy and nutrients around the globe and dictating climate patterns everywhere from the equator to the poles. Here, frigid water sinks beneath the surface, carrying both heat and carbon deep below, fueling the powerful global ocean conveyor belt that drives ocean currents worldwide. The Southern Ocean is truly the engine room of our planet, deciding how much carbon is locked away in the deep or released back into the atmosphere, influencing the pace of climate change. Its upwelling waters bring nutrients to the surface, supporting vast blooms of phytoplankton, tiny plants that absorb CO2 and form the foundation of the marine food web, feeding everything from krill to whales. When these microscopic organisms die, some of them sink, carrying carbon with them to the deep ocean, where it can be stored for centuries or even millennia. The efficiency of this biological pump depends on the Southern Ocean's unique mixing and circulation, which stirs nutrients and carbon through its vast, swirling eddies. Any change here, whether in temperature, wind, or ice, can ripple across the globe, releasing or trapping carbon and either warming or cooling the entire planet. To truly understand Earth's climate, we must look south, to this powerful and mysterious ocean that shapes our world in ways we're only beginning to grasp. The Southern Ocean is the master regulator, holding the key to the lukewarm interglacials of the past, and perhaps to the stability of our own future climate. Its balance is delicate, its influence immense, and its future uncertain as our planet warms. The fate of our climate is tied to the pulse of this great ocean, a pulse that beats at the heart of our living planet. How did the Southern Ocean keep Earth cool for so long? The secret: stratification. Picture layers of water, like oil and water in a glass, refusing to mix. During the lukewarm interglacials, a stable surface layer formed, capping the deep, carbon-rich waters below. Normally, upwelling brings this deep water and its carbon back to the surface, releasing CO2. But stratification stopped this process, trapping carbon in the abyss. With less CO2 escaping, the atmosphere stayed cool, reinforcing the ocean's layered structure. It was a self-sustaining cycle. Cool conditions maintained stratification, which kept carbon locked away. The Southern Ocean had put a lid on global warming, controlling the planet's thermostat from below. This discovery revealed the ocean as an active force in climate, not just a passive reservoir. The way its waters are layered can reshape the atmosphere. The stratified Southern Ocean explained the long-standing puzzle of the lukewarm interglacials. The power to cool the planet was hidden in the structure of the sea. Stratification wasn't the only player. Sea ice was crucial too. During the mid-Pleistocene, more sea ice formed around Antarctica each winter. This white blanket reflected sunlight, reinforcing the cold and helping more ice to form, a powerful feedback loop. Sea ice also acted as a barrier, blocking gas exchange between ocean and atmosphere. It sealed in carbon, adding another layer of insulation atop the stratified ocean. The ice calmed the ocean surface, reducing wind-driven mixing and preserving the delicate layering below. Together, sea ice and stratification formed a partnership. Ice encouraged cool, stable layers. Stable layers kept carbon trapped. This system kept atmospheric CO2 low and the climate cool. The Southern Ocean's icy shield was a perfect natural mechanism for keeping a lid on planetary warming. For thousands of years, this partnership maintained Earth's lukewarm pause. The interplay of ice and ocean shaped the fate of the planet. The idea that the Southern Ocean was once layered and stagnant was a compelling theory, but science needed more than speculation. It needed hard, physical proof, something tangible that could be measured and tested. That answer came from an unlikely place, a thin crust of rock on the Hawkesbury Seamount, a remote underwater mountain rising from the depths of the Southern Ocean, far from any continent. For millions of years, the deep Southern Ocean waters washed over this rock, leaving behind chemical traces, layer by layer, like pages in a history book written in stone. Scientists drilled a core from the crust, extracting a long, cylindrical sample that revealed a timeline of ocean chemistry stretching back over 1 million years, an unbroken record of the ocean's past. In the lab, they focused on neodymium isotopes, rare elements that act as unique fingerprints for different ocean basins, allowing scientists to trace the origins and movements of ancient waters. During the lukewarm interglacials, the isotope patterns revealed that the deep water was much older and more isolated from the North Atlantic than it is today, suggesting a dramatic shift in ocean circulation. This was the smoking gun, clear evidence that the global ocean conveyor had changed course, and the Southern Ocean had become more stagnant, cut off from the rest of the world's deep waters. The data matched the stratification theory perfectly, confirming what many had suspected but never proven. The Hawkesbury Seamount's chemical archive provided the missing link, confirming that the deep ocean structure had shifted dramatically during these ancient periods. The Southern Ocean's isolation explained the missing carbon, the mysterious pause in global warming, and the planet's cool, stable climate during those times. Science had finally found its proof, written not in words, but in the ancient layers of rock beneath the waves. The story of the lukewarm interglacials was no longer just a theory. It had become a fact, grounded in evidence and discovery. The ocean's hidden history, once locked away in stone and silence, had finally been revealed to the world. The story deepened with another clue: lead isotopes in the seamount crust. Lead isotopes trace the origins of water masses, distinguishing between North Atlantic and Southern Ocean sources. During the lukewarm interglacials, the lead signature pointed to water from the Pacific and Southern Oceans, not the North Atlantic. This meant the deep ocean was dominated by southern-sourced, isolated water. The global conveyor's northern engine had weakened, and the Southern Ocean was cut off. Neodymium showed the water was old and isolated. Lead showed it was southern in origin. Together, these chemical tracers painted a picture of a fundamentally altered ocean. The planet's circulatory system had shifted, changing the climate for hundreds of thousands of years. The whispers from the deep, captured in rock, revealed a secret of global importance. The ocean structure had changed, and so had the world. The lukewarm interglacials ended around 430,000 years ago with the Mid-Brunus event. Suddenly, interglacials became much warmer, and atmospheric CO2 levels jumped. The evidence showed the Southern Ocean's stratification broke down, the lid was lifted, deep carbon-rich waters mixed with the surface, venting CO2 back into the air. This carbon release pushed the climate into a new, warmer regime. The trigger is still debated, but likely involved changes in Earth's orbit, sea ice, and wind patterns. The Southern Ocean's ability to trap carbon diminished, and the planet's climate shifted dramatically. This transition highlights the sensitivity of our climate to ocean dynamics, not just orbital cycles. The Mid-Brunnes event was a planetary turning point. The lukewarm interglacials were a unique phase, ended by a fundamental oceanic shift. When the ocean changed, so did the world. The lukewarm interglacials offer a warning for today. The Southern Ocean still absorbs much of our excess heat and CO2, slowing global warming, but rapid greenhouse gas emissions and Antarctic meltwater are changing the ocean's structure. We may be recreating the conditions for intense stratification, just like the ancient lukewarm era. A stronger ocean lid could slow natural CO2 release, but also weaken the ocean's ability to absorb our emissions. A stratified ocean is less productive, threatening the Antarctic ecosystem and global climate stability. The ocean's help is not guaranteed. The past shows that changes in the Southern Ocean can have global consequences. We must heed this ancient warning. The story of the Southern Ocean is one of connection and balance. Changes at the bottom of the world can reshape the entire planet. The ocean is not just a victim of climate change, it's a powerful player. Our actions now threaten to push this system toward a tipping point. Protecting the Southern Ocean means preserving Earth's stability. We must act as stewards, recognizing that our fate is tied to the ocean's health. The lessons of the lukewarm interglacials demand humility and foresight. The future of our world is in our hands.